see. Okay, so am I live yet? Oh, it's still not running, is it? Redundant transition. What the hell does redundant transition mean? Well, okay. I think I'm live now. Right, this is just a preliminary test because I've got some problems with my pulleys, and I'm printing new pulleys at the moment. Right. Well, I'm running this on not the full 12 volts. I'm using 2 lithium ion, 2 pairs of lithium ion cells in series. I need to get my big power supply out of the cupboard because it's variable and I can adjust the speed, which is what I really want to do, because my little regulated current limited power supply over here it can't drive more than 500 milliamps, which is about half an amp. And the problem is, using a high torque motor, this high torque motor really requires about an amp to 2 amps or so. It depends on really on how much power I put into it really. But I just did a little test a minute ago, and I've got one coil populated. Got my RPM meter hooked up to the sensors there, and I've got a magnet on the end to detect the speed. A full wave bridge rectifier connected to the coil. Full wave bridge rectifier is connected through this red and yellow lead, which is positive and negative, to this LED display. Right, that's all I've got. So there's a room for another. There's total population of a total population of 12 coils can be. Well, I can put more than 12 in actually. I can put 16 coils in this unit. The way it is at the moment. If I want, I can have up to 16 coils. But at the moment I've only got one coil in, right, because I just slide them in, you see, easy peasy. Well, one coil in, and I had this up to about 8,000 RPM, and my LEDs light really brightly, and the RPM doesn't seem to change. Now I'm holding the phone right now, so I can't do very much. I'm one-handed, remember. I'm holding the phone, the camera, the whatever. So I can only really show you some basic tests right this minute, which is okay. So first test, I'm going to run it through this resistor, so this big resistor here, so that we're limiting the voltage and current. So it's going to be about 3,000 RPM. So let's do a little test with, I'll turn that light off. Let's do a little test at 3,000 RPM or something like that. And there's the LEDs coming on. We're about 4,000 RPM, 4,400 RPM. And we've got just a few LEDs lit at the moment. Now let's just disconnect this at this speed and see if there's a change in the RPM. It's still dropping because the battery's running down. Now let's connect the LEDs. Oh, the RPM is still dropping because these batteries are running down. I need to get my power supply out of the cupboard. But it's interesting. Notice that when I connected it, there was no change. Now let's just give these batteries a minute to rest and recover, and then we'll give it the full whack of up to 8. Well, I don't know if I can get up to 8,000 RPM because the batteries are running down. I'm charging another set of batteries up over there at the moment. I've got them on my lithium-ion balance charger, so I'm waiting for those to charge up a bit. Now this will be a pulse test, so I'm going to take my clip off and I'm just going to do a pulse test directly on there. So the LEDs are connected up still. Let's go to for the full whack. Right, the belt could come off as well because that's where I'm printing new pulleys. So let's try this. Right, RPM meter in. Right, here we go. 6,000 RPM is the maximum we can get to at the moment. And we're consuming 3 amps. So that's it for now. So I'm drawing about 3 amps out of these batteries. I don't want to overload them. That's why I need to get this power supply out of the cupboard, because it gives me some variability. I've got variable controls on it, you see, and it's something I made a long time ago in the 1980s. It's a bit of a monstrosity. I basically used an old steel amplifier, a valve amplifier chassis to build my power supply into it, and it's a bit of a monster. I'll have to dig it out because it's got all the it's got dual outputs, it's got loads of protection in it, it's got thermal protection, overload, short circuit protection, it's got current measuring on the built into it, so you can actually see how many amps I'm drawing from it. So I have to dig that out of the cupboard at some point. But I'm going to continue to build this for now. I've got more coils I need to slide in and fit. I need to sort the pulley system out, and then we can have some fun, because I disconnected the LEDs, and as you was looking, it didn't seem to make any difference. However, the batteries were dropping anyway. The battery voltage was dropping, so it's hard to tell. This is why I need to get the power supply out of the cupboard, because then I can work with a stabilized fixed voltage, which isn't going to keep going up and down all the time, because the batteries tend to vary because of as they start to discharge. These are old laptop batteries, so they're not very efficient. They don't hold much of a, they don't really hold that many amp hours. I think these batteries are about 1.5 amp or maybe 2 amp hours, but they're old, so they're not full capacity. They don't hold the full capacity. I'm always checking them to make sure that they're not getting too warm as well. They're fine, they're cool. They're not hot. If they were hot, I would get rid of them, because it means that they're thermally unstable. I mean, when you're drawing 2 amps, they shouldn't get hot. Obviously, they would get hot if you drew too much power out of them, like maybe 10 amps, which is not something you shouldn't really do. Anyway, so I just thought I'd show you where we are with this at the moment. Yeah, my belt was starting to ride up again, so this is why I need to get these new pulleys on here, because the belt came off a couple of times. But the system's working anyway. My design's working. It's just that I've got a little bit of tweaking to do on the tensioner, the belt tensioner, which is this thing at the back down here. When I initially started to drive this, there were brand new bearings I put in, and they were really stiff. They were really tight, and it took a lot of power. I was pushing like 8 amps just to get the damn thing to turn. I mean, because it was just stiff, you know, because it had just been assembled. Now it turns easy peasy. It really turns easy now. It's a lot better. It's eased itself off a bit, which is a good thing, because the bearings need to be running a little bit, because it's they're packed with grease, you see, and because the grease is so tightly packed in there, it tends to cause a lot of friction, well, slowing down, because you're pushing that around as well. Anyway, they seem to have eased off now, and I've also been trying to balance it out because these 4 drums that are inside, the rotary drums, right, that are going around there, there's 4 of them, and I can turn one of them and it locks into the other pole, because they tend to latch because of the alternating. So that one's put south, one's north, then south, then north. They alternate, you see. So I've been offsetting them so that I can basically balance the system out, because they were kind of vibrating really badly in one position. But I've got them in a position where, by twisting one and adjusting the other one and turning around, I've basically got the whole drum assembly balanced out pretty well now. It's really good, actually, but it's not perfect. It's good enough. I've had it up to 8,000 RPM, and it was working quite happily at 8,000 RPM. It went through a vibration cycle at about 7,000 RPM, where it started to resonate, it started to oscillate, and the whole thing was just vibrating. But once it got past that point, once it got a little bit faster than that, it was quiet again. So yeah, once you get certain resonant frequencies, it just plays havoc with everything. So it's important to stay away from resonant frequencies, otherwise I'll just shake the damn thing to pieces. Anyway, so it was running really well at 8,000 RPM until the battery started to die. It wasn't drawing that much current either. It was only drawing about 3 amps, which is surprising. And it was actually drawing 3 amps when it was running a lot slower. So it's obviously because once you get to a certain speed, it seems to actually run even better. I don't know what's going on with it. But yeah, I don't seem to be having a big drag problem now. It seems to be much more stable. Yeah, I'm kind of chuffed and excited about it, because it's something I've been working on my previous build for a long time, and it was just such a pain because every time I made something, things were flopping about, and I kept getting the rotors moving and warping because of the plastic. But this drum system is so much better. There's because it's tight and because the drums are so small, and there's actually 2, 4, 6 sets of magnets basically in each drum, and there's 3 magnets in each group. So there's a group of 3 magnets, well, like these. Right, there's 3 of these basically stacked on top of each other. There's only 2 on here, but there's 3 of these. Right, so there's 8 sets of 3, and they're in the drum, and and they're staggered, so it's basically south, south, then north, north, and south, south. So we have a wide area of south field and a wide area of north field, and because of that, as they're rotating, we have less lens drag, because the south field is pretty much at a 45-degree angle, more or less, before the north field kicks in. So it's got a real fast switch. It basically switches very rapidly between one pole to the next pole. So this steep change in polarization seems to make a big difference, because we don't have as much drag. And also the coils are set a long way back, and I can't get the ball bearings in there at the moment. I was going to put ball bearings in to improve the coupling, but now I don't think I need them. I'm not sure if I actually need them, to be honest. There's the coil above the rotors. Let's just turn the rotor a bit. You can see the gap. The gap is massive, but it seems to be working pretty well, considering there's a massive gap there. I mean, Jesus Christ, look at the gap. That must be, I don't know, let's measure it anyway, actually. I've got my calipers, and it was lighting them LEDs up pretty well as well, considering. Now let's get my calipers in here. Got my calipers on the rotor. Oops. I'm just going to push this down until I can get to the height. Right, let's just put the camera on there. Bring my calipers down till I get to the same height, which is about there. So the gap between the magnets and the coil is basically 12. It's about 12 millimeters. And I actually have them LEDs lit really brightly as well, which is quite surprising at 8,000 RPM. Yeah, which is a good thing, because it means I've hit the resonant frequency. Basically, it means I've hit resonant frequency of the coils, which is what I was trying to get to. Anyway, that's it for now.